Barely Berry Jr. here, back for some more physics. I'll do a slight change in pace and do some undergraduate physics. So I have actually 2 exams tomorrow. I have a graduate level and my foundations class, which will cover undergraduate level. So I'll cover some undergraduate to cover that. So getting everything set up now. Figured I'll just log on while I'm setting up. And we'll go ahead and take a look at everything. So I have, and actually, I just remembered I didn't watch a video on one of the ones I need to do. I already sent it to myself. I didn't actually watch a video on one that I need to watch. In undergraduate, I did the what do you call it? Coupled pendulums, but I haven't done that in a while, so neglected on watching a video for it that professor put out. So I need to watch that. So I think I'll cover these 2 problems I'll cover right now, and then I'll go ahead and watch that video. So that should still give me 2 good problems to do. All right. So I'll be up and running momentarily, and we'll get started with the problems. In a angular acceleration, which I believe I'll put in the title, and angular. I have this muted already. Testing, testing. As long as y'all can hear me, we're good. Boom. So I'll alter the problem slightly and just look at the concepts and see where it goes. Right. Let's go ahead and see what this looks like. Don't have the book open today. Don't need 4 at the moment. So I'll just go ahead and just stream. And should I turn the vid sideways? No, I'll just leave it upright. So it's 9:25. And the first thing we'll look at, let me change my scrolling text. Notice this thing doesn't click sometimes. So classical mechanics, angular, and statics. Boom. That seems to be about perfect. Awesome. So the idea is that we have an object that's rotating. So it could be any object, a CD or a merry-go-round, or they call it different things, but it could even be square. It doesn't even have to be circle, even though it's more descriptive for it to be circular. But I'll make it square in this moment. And let's say that the object that's rotating, this is the center of mass, it starts from rest, and let's say that it accelerates at, let's say angular acceleration is 2 uh, radians per second squared. Right? And let's say that we have an object sitting on it. Let's say that object is 3 meters apart. So we'll call 3 meters equals r. There's an object that's sitting on this thing 3 meters away from the center of mass. That's the part where it's rotating from. And let's say it has a coefficient of friction, static friction. So let's say the coefficient of static friction is 0.55. Right? So let's see what things we can learn about this object. So first thing we do is label everything. We have alpha as 2 radians per second squared. Friction. And do I have the mass of the object? I don't have the mass of the object. Now, one thing to keep in mind is, and we'll just talk about the different things you could be aware of this system. So again, we have this square merry-go-round, let's say. It's starting from rest. Somebody's starting to push it. It's starting to gain speed at 2 radians per second squared acceleration. So what that means is that, so if you have a circle, 1/4 of the circle is pi over 2. And so basically, if it turns a quarter of the way, that's pi over 2 radians per second. If it turns out that way continuously, pi over 2 is what? That's 3.14, just about, divided by 2. So that's just about what? 1.6, just about, somewhere around there. So what that means is this object, the first second is rolling just over a quarter turn, like it's spinning just over a quarter turn, but is accelerating 2 radians per second squared. So every second it goes 2 radians per second faster. So after the first second, it's going 2 radians per second. After 2 seconds, it's going 4 radians per second. So after 2 seconds, it can turn, it's going at about a half a turn per second. After 3 seconds, it's going 6 radians per second. So it's about 3/4 of a turn and so forth. Well, no, 6 is almost pi, almost 2 pi. So yeah, so I'll go at 3 seconds, we're going almost a full turn a second. So picking up pace pretty fast. That's the first thing we notice. If we want to talk about the force that's being imparted to this object from the spin, we can go to Newton's laws, which is F equals ma. Force equals mass times acceleration. Newton's second law, if I recall. And let me increase the size of the pad some. So we can go ahead and use Newton's second law. But the thing about this is when you have an object that is spinning and accelerating, there's 2 times of acceleration. There's the centripetal acceleration and the translational acceleration. So we can have m a t or ac plus a t. So you have both of these types of acceleration when something is accelerating while spinning. So my understanding is that the centripetal acceleration is the acceleration that's going inward from the object. So, like if you have a or like a ball attached to a string, and you rolling that ball around, your hand in the rope is causing a centripetal force because it's pulling inward. So there's basically as centripetal acceleration is accelerating directly towards the center. So let's say if a object is going in a perfect circle because of some kind of force, it starts going at a translational motion and then it starts going in a perfect circle. That means there's a force pushing directly inward towards the center that's causing that thing to spin like that. The net force is causing it to go in a circle. So I've actually seen this demonstrated one time. So you can find a video on YouTube where someone like knocks a bowling ball straight, and the professor or teacher runs around the outside of the ball, and he just hits it with a hammer directly towards the center. So the first time he hits it, it goes a little bit that way. Then he's running with it, so he's steadily hitting it, and he's just steadily tapping it, and you see it goes in a nice perfect circle. And he's just tapping it straight directly on its side. So he's not trying to angle it to turn. He's just tapping it directly inward. And when he taps it directly inward, it just makes a nice smooth curve. And as long as he keeps that consistent tap, it just makes a nice big circle it was like the gym floor he was doing it in. So they made a big circle. That's the centripetal acceleration. And the translational acceleration is simply the fact that if it's accelerating, it will go faster in this direction. So, the forward motion of it in its instantaneous position, it'll be going faster every second, like we mentioned before. So this would be AC, and this will be AT. And the resultant acceleration, I'll just call it A, will be going pretty much in that direction. It'll be a resultant vector that's the sum between these two vectors. So we needed to know this to solve this problem. Now, looking at the two types of acceleration, it equals m. So centripetal acceleration is the translational velocity squared over the radius plus, and that's the magnitude of it. The translational is going to be the angular acceleration times r. So this, I don't remember the derivation for this, but it just comes from the angular acceleration field. I'm pretty sure I saw the derivation at one point, but I don't remember what it is. And if we look at the translational acceleration, so basically what's going on is you have, in this case, I called it, well, I didn't really call the angle anything yet. So let's say that as this thing moves in this direction, let's call this angle phi. So as that angle accelerates, as that angle gets larger and larger by second, the point up here will be moving angularly as fast as that angle is opening, but it'll cover more ground the farther out it is. So if it's very close to the center of mass, it's just going to make a smaller circle in the same rotation. But as farther out, it's going to make a bigger circle, which means it's going to cover more ground. So if we multiply the angular acceleration by r, we'll get meters per second squared. So it'll give us the distance that is actually accelerating through. So it's of note that radians are unitless. So we call them radians, but and I mean they're a thing, but they don't have a unit as far as like seconds or meters or anything. So that's another reason why we need the R. So it all works out that the R supplies the m to make in meters over a second squared. And if you look at this, we see that velocity squared is meters squared over second squared. You divide it by the radius, which is m meters. So now you have another meters over second squared. So the units match, the units work out. So one thing about physics, you have to make sure that the units work. All right. So we can say that if we want, let's say, all right, so let's look at this detail. So we don't have a mass, but we do have the coefficient of static friction. And the coefficient of static friction is going to be related to the normal force. So the normal force of an object is going to be the object that's pushing up from a surface and stopping it from falling through the surface. And that normal force is going to be the same thing as the mass times the gravity. So whatever, and this is Newton's third law, if I recall, it is an equal and opposite. If there's a force pushing on an object, that object is pushing back, always pushing against it equally, equal and opposite force. So basically, this is mg, and this would be n. And the way friction works into that, friction equals the coefficient of static friction times the normal force. So in other words, it'll be some fraction, and I don't think it could be more than, if it's more than, then it'll be actually sticky. So I guess it could be more if you put something sticky there. So it's actually sticking onto the thing. But the idea is that it'll be some fraction of the normal force. So if there's no friction, then when you started spinning this thing, then the ball, whatever this object is, would just stay in one spot. It'll just stay there because there's nothing to make it be pulled along. And the greater the coefficient of static friction, the more it'll be pulled along, the less it'll slip. And welcome all who joined. Let me know if you have any questions or comments. I'm checking the live chat, so I'd be happy to respond if you have any questions or comments. So what we can do is, let's say we wanted to know how fast this thing can spin before the object slips. We need to know how much acceleration can the friction that it has maintain or hold. Right? So we can say that the force of friction is going to be m acceleration. Newton's laws are going to always hold. And in this case, it'll be modulated by the coefficient, right? So, which is basically this is what we have here. So this is n mg because the acceleration is going to be gravity, and we know that this force has to be surpassed by the other force if it's going to slip. So in other words, as long as F, I'll call this F R for F rotation, as long as F rotation is greater than F friction, then the object is not going to slip. So if this thing is spinning slow enough that the force of rotation is less than the force of friction, then it'll stay there. At the moment that the um, force of rotation is less than the force of friction, then the object will slip. So we can say the force of rotation has to be greater than the force of friction. So we can say that MAC plus AT has to be greater than mu S mg for the object to slip. So we want to find out when this object will slip. We can simply solve this equation and solve for accelerations and find out when that'll be. So we know we don't have the mass, but the mass cancels. So the good thing about gravity is it pulls on all masses the same. So oftentimes masses cancel in these equations, which makes it very convenient. Sometimes when you're doing problems like this, the professor might give you mass, and sometimes it can be considered sort of a trick to, in a sense, get you to waste time on things that you don't need to waste time on. So be careful with that. I guess it depends on the context. I mean, I hate to say that they're trying to trick you. I remember when I was a learning assistant at UT, my undergraduate school, where I got my physics degree and astronomy degree. I was a learning assistant for an EM class multiple times, and I remember one of the students complaining that they felt it was a trick question because they were trying to get the magnetic field around some object or what have you, and they gave information that wasn't quite necessary to solve for the electromagnetic field, and the person felt like, they're tricking me. But he was an electrical engineer, so I brought it to his attention that if you're building a machine, the device has to fit into the machine. So even though the electric field might be based solely upon, let's say, the strength of the electricity going through it or whatever, I don't remember the exact problem. But suffice it to say, if you're building a machine, well, I mean, you still have to make sure that the part fits. So depending on the context, it might not necessarily be a trick question, but you might be given some superfluous information. So now we have AC plus AT must be greater than USG. And we can figure out what that is. So I called the coefficient of static friction 0.55. There's always going to be some decimal. And G is 9.8 meters per second squared. So maybe I should have picked an easier number. Can't do that one in my head for sure. So I'll get some, I could just like round to 10 or something, but I'll just go ahead and get some relatively accurate numbers so we can see what these values are like. As far as my calculator, the other day we had an exam. Say the other day, last week, because we had an exam last week as well. Like I said in my foundations class, we have an exam about every week because we were covering as a review all of undergraduate physics, pretty much all the major parts, definitely. And they expect us to really know the stuff mostly. We just like filling in our gaps, so it goes pretty fast. So that's 5.39 meters per second squared. So that means that as long as the two accelerations together, when you add their vectors up, or their magnitudes up, as long as it's less than 5.39 meters per second squared, the object won't move. If it's greater than 5.39 meters per second squared, the object will move, will slip. So we can go ahead and plug these things in and say translational velocity squared over r plus alpha r must be greater than 5.39 meters per second squared. And let's take a look and see how we can solve for these components. So we have r, we know what r is. we're actually given the angular acceleration, so we have that. All we need to do to finish solving the problem is get the translational acceleration. So the translational acceleration is going to be, the translational velocity, I meant to say. You can actually utilize the definition of angular acceleration. Centripetal acceleration. So what I'm going to do, I'll take these two things out. And again, centripetal acceleration, that's the definition. Now, the thing about angular acceleration, it has counterparts to the linear acceleration. I still don't remember the angular formulas, but I do remember the linear ones. So we have, for instance, x of t equals 1/2 gt squared plus VOT plus x naught. If I take the derivative of that, so we have x dot t equals gt plus v naught. Or I'll just say at plus v naught. So this allows us to get the velocity, the linear velocity. So the counterpart of this would be and actually, that's it. So translational velocity is going to be the acceleration t times v naught. And what I'm going to do is I'm going to alter this equation, instead put in angular acceleration t plus angular velocity. And now I'm going to make this equal v t squared over r. So basically what I'm doing is just substituting the equivalent equation in angular form to solve for the variable I'm missing, right? So now I can go ahead and get what I need. I guess this is, what we call this velocity. I don't know what we would call it. We'll just keep it as v dot. Terminology of this stuff is kind of tricky sometimes. So that means that r alpha t plus omega equals v t squared, and omega is the translational velocity, and this is going to be w naught, just like in the initial equation. We know that w naught equals 0 because it starts from rest, so there's no initial velocity that adds. It doesn't have a bump. It just starts from 0 and then starts accelerating, so we don't have to worry about any initial velocity. So r angular acceleration t plus equals v t squared. So that means that the translational velocity equals the square root of r alpha t, where r is the radius, alpha is the angular acceleration, which we have, and t is the time. And let's see here. Make sure I didn't miss anything. Everything look. Okay. What I did wrong. Maybe they can put a squared on this. There shouldn't be a squared there. So this is velocity. All right, so let's see if there's anything else I'm missing. Let me make sure I'm clear about this. So, angular velocity is radians per second. So, in order to get the angular velocity from the translational velocity, we divide VT by R, so that's meters per second divided by meters. So I get the 1/2 that is essentially the units of angular velocity. So we have that. And there we go. So actually I shouldn't have taken the square root. It should stop there. So now going back to our equation, we needed VT squared. So if I do VT squared, it's going to be R alpha T plus omega. Oh, I forgot omega not a 0. R omega T squared. So that'll end up being R squared alpha squared T squared. Well, I might as well just keep them the same and just square everything. All right, so that's good enough right there. And if I miss anything, I think I'm good. Right, that seems okay. So now we have our VT squared. So, and let me actually make this all a different color because this was all on the side. So this will stick out. So now all I have to do is plug, and this is part of that. So we did that to get VT in terms of A. So now I can go ahead and plug this in. So I can say that RAT squared over R plus alpha R must be greater than 5.39 meters per second squared. And what I'll actually do is find out how much time must pass in order for this to happen. So how much time needs to pass for the acceleration that we have to be greater than the acceleration that we're looking for. Let me check and make sure I didn't miss anything. Or squared. Right, everything looks good, I believe. So I only have time in the first part. So what I'll do is I'll solve for t. I'll say that r. So I'm going to cancel out the r's there. A squared t squared must be greater than 5.39 meters per second squared minus AR. So we can say that t squared must be greater than 5.39 meters per second squared minus angular acceleration times r divided by angular acceleration squared t squared. And then when I take a square root of that, I'll just copy everything down. So we can say that the time given this acceleration for that block to flip off must be greater than that. Now let me check and make sure that my units work out. So I have meters per second squared here minus meters per second squared, because again, this is 1/2 squared and this is meters. That's the radius. Divided by, this is 1/2 to the 4th, because it's 1 per second squared, and then second squared. So this equals 1/2 squared. And I think I am missing something on units. Let me see. For second squared. All right, let me see. I think there's something off with my units. Oh, that's what it is. Oh my gosh. Should be radians per second squared. I think I'm putting in the meters where I shouldn't. Let me see here. Divide. Oh, that's what it is. I made a mistake and wrote chi squared instead of r. Oh my gosh. So that was just a typo. I was looking, I had an extra m there. That's because this is r and not t. So that's why that wasn't working. So this is meters. So now I have what? I have the meters will cancel and the second squared will cancel, and this will leave 1 over second squared in the denominator. And if you have a fraction in the denominator, it flips and becomes second squared. And I'm taking the square root of all of that, so it equals seconds. So we see that if this equation is correct, this is going to give me time in seconds. So all I have to do is plug everything in, and I'll see what the time needs to be greater than. So this will be the square root of 5.39 meters per second squared minus, and we gave that 2 radians per second squared times, and the radius I gave, this distance from the center was 3 meters, divided by, so that's going to be the acceleration squared, which is 2 radians per second squared, and then we have the radius again, which is 3 meters. So let's see how long this thing has to accelerate before that block will break off or fly away, move, given the coefficient of static friction and the rate of acceleration. We'll have 5.39 minus 2 times 3 divided by 2 times 3. And let me see. So I think maybe I just gave it bad values. So I'm seeing a negative there, which it shouldn't be. So let's see what else I may have done here. Got that. VT squared is RT. Acceleration time second. Second. Two, three. Well, maybe I just picked some bad numbers. So I think about making up a problem. See what I did. I have to square this. Is that it? Let's see. Nope, that still gives me a negative. Let's see. Even though I did forget to square that though. So one more thing. Might have just gave myself bad numbers. What would make these numbers work? I guess if my radius was smaller. So why don't we do that? Why don't we make this radius 2.5 instead? And let me see what else has to change somewhere. I think that's it. All right, so let's see now. I need to change all of those to 2.5 and 2 squared, 2.5. Right, well, that's right, yeah. I just gave myself bad numbers. But the numbers I gave, it ended up being 0.2 seconds. So given and I think what it is, like I noticed in the problem that professor gave, the coefficient of static friction was a lot bigger. His was 7.75. So my coefficient of static friction was only 0.55. So yeah, I just gave myself bad numbers. So at a 0.55 coefficient of static friction, it doesn't take much for something to move. That's good to know. So I think that's what threw me off. If I would have tried to increase my coefficient of static friction, then I would have had to change a few things. I guess I just had to change the acceleration. I had to rewrite that a few times. But there we have it. So, but given a coefficient of static friction of 0.55, acceleration 2 radians per second squared, with an object 2.5 meters from the center where it's spinning, all you need is 0.2 seconds and the thing will start moving. So we covered the acceleration, how fast it's starting to pick up speed earlier. So it's starting to pick up speed pretty fast, pretty much like a quarter of a turn and a half a turn a second. So yeah, it doesn't take long for that thing to start moving. It'll start moving almost immediately. All right, that's that. Now the next one will be a little more fun. So we'll say that we have a object that's attached to a fulcrum on the wall. So let's say this is a beam, and we have a weight that's hanging from the beam. So let's say this weight is one of those big, you know, metal globes that people use to exercise with. Let's say it's one of those. And let's say that let's say that is being anchored by a tension wire at a certain distance. I'm probably going to give myself bad numbers again, but we'll just work with it. Well, let's say that this is 50 degrees. And let's say that up to here, where it's meeting at is 7 meters. And let's say that the beam itself is 10 meters. So we'll call that L, the total L is 10 meters. What else can we say? So we have 7 meters there. The whole beam is 10 meters. Let's say that the mass weighs 20 kilograms. You got L, we have the angle, and let us say one more thing. Got the point from there. So why don't we find out what the tension is? So I think with all the information that I have here, I could find out what the tension is on the wire here. So T is what? So we have theta equals 50 degrees. L equals 10 meters. The sharp part here we'll call little l equals 7 meters. Oh, we need the mass of the beam. Let's say the mass of the beam is, let me see. Let's say the mass of the beam is 30 kilograms. So the mass of the actual thing that's attached to the wall. Let's say the mass that's hanging, we have that down. That's 20 kilograms. And let's go ahead and find what the tension is on the wire. So the first thing we need to do is determine the nature of all the forces at play in this situation. So when we look at this, we can see that there's F, the force of the mass going down here, Fm. There's the force of the beam coming down from the center of the beam, Fb. That's everything that's going down. We have a force from the wall here because the beam is not sliding down the wall. It's not going into the wall, not coming out the wall. So there's some force there. And there's some tension, which we want to find out what it is. But given that this is a wire, we know it's pulling, it's not pushing. So there's some tension going that way. And this is just F. We can call it FB, but I already called the weight of the beam FB, so we'll just call that F. So those should be all the forces: the wire, the wall, the beam, and the weight. So what we have to do now is break each of these into their X and Y components. So on the X side, we know that all the forces are going to be 0. So we have Fx, which is the S component of this. We're assuming that this thing is, operating on in the two-dimensional plane. We have the X component of that. And that is pushing out to the right because the tension is pulling in. We have minus Tx minus the tension that's pulling inward. And I believe that will be the only horizontal forces. We have in the y, we have Fy, and that's also going up because it's holding the weight up. We have plus Ty because the tension on the wire is pulling the weight up. And we have minus Fm since the weight is pulling down. And we have minus Fb since the mass of the beam is pulling down. And that also equals 0. So the reason why this is called a statics problem is because the object is stationary, is not moving at all. So that means that all the forces, the net force on the object has to be 0. So F equals MA equals 0. And this is F net because it's not moving. So that's why we can't use Newton's second law for this, because there's no movement. Thus, there's no acceleration. So if it was static and then began to move, then it would be acceleration, but there's no movement. So there's no acceleration. It's just static. So we can't use Newton's second. But these are all the forces. And we want to find the tension force. So we're going to have to find the X and the Y components of tension. So I can say that Tx equals Fx, and the X tension will be, so basically cosine of theta equals Tx over I was about to say I can't use yeah, I can get the link to that. So let me back up. Well, hold up. Let me just call this cosine of theta equals the L over the T. Yeah, L over T. So I think that's what I need. Is that what I need? No, cosine of theta is Tx over T. So Tx equals T cosine theta. That's what we need. So the tension that's pulling, the cosine of that angle, being that it makes a triangle with this part here, where the angle is, you know where it's connecting at, the tension, the cosine of that tension with the angle that it makes with the horizontal is going to give us the amount of force that's pulling in the horizontal. So, and I'll make this like so. And we could also get Ty out the way now. Ty equals T sine theta. So we will have that there for when we need them. So Tx equals T cosine theta, which equals Fx. And did I give myself enough information? Let me see. Maybe I didn't. All right, so we're gonna have to solve the other one first. Is what it is. Let's go back. So let's try Ty equals F beam minus Fm plus Fm minus Fy. Let's see if we can get the Ty component. And we can parse out from there. So F beam is going to be M beam G plus F mass is going to be mass G minus Fy All right, so I may not have given myself enough information. Let me see. That's what it is. I'm missing one equation. Let's back up one more time. We have to get the torque equation. So the torque is actually the force so basically I have all of these sort of linear forces. The mass is pulling down directly straight. The beam is pulling straight down. The force of the wall is pushing out and up. The tension wire is pushing up and to the left. There's also a spinning force, a torque. And this is going to be like so. So the force of torque of the beam is going to be the weight of the force of the beam times 1/2 its length. So the length of the beam is L. It's going to be FBL over 2. So that's a torque or spin coming from the beam itself, wanting to make basically pulling on the tension wire and wanting to fall down from the wall. So FBL over 2 is the tension from that. We have the mass, which is on the edge of the beam here. That's going to be wanting to make the thing spin, like they're going straight down, but as far as the wall and the beam is concerned, is wanting to make it spin. So basically, torque is always going to be a force times a distance or times a meter. So we're going to have F mass times, and I call that length, that full length L. We have that. And then we have another torque. It's going to be the tension wire itself. And we can say that that torque is going to be the part that's pulling up, because the tension wire is pulling up and to the left. So the left component of the tension force is not making it spin, is making it go straight into the wall. But the upward portion of the tension force is making it torque, just like the weight is. So there's going to be a plus. It's going to be from where it's hitting or touching the beam at. So again, there's always going to be a force and a distance. So it's going to be L. And as we discussed before, the vertical component of the tension is T sine theta. Let me actually put that elsewhere. Since I erased it down there. So we have T equals Ti plus Tj, or Txi plus Tyj, and sine of theta is the Ty over T. So Ty equals T sine theta, and therefore Tx equals T cosine theta. So I'll leave that there. So now we need the y component of the tension. So I could have written it as Ty, but I just put what it is there, T sine theta. And now we have all of the equations. So it is necessary to remember that for a static problem with a beam and a weight, a tension string, we're going to need the x forces in the horizontal, the y forces in the vertical, and the forces of spin, because there's going to be some spin since it's basically a fulcrum. So now let's see if I have everything I need to solve for something here. And I believe I do. Oh, and it's going to equal 0 because the static, the thing is not moving. So all of these forces, when they add and subtract with and against each other, they're going to balance out. So that's something good to remember. X, Y, and torque for these static type problems. So now we have LT sine theta equals FML minus FB L over 2. Oh, and now we can actually solve for tension. We can solve for it right now. So we have P equals FML minus FB L over 2 divided by L sine theta. There we go. We have the tension, which is what we were looking for. And we didn't even need to, get the components and add them together just by remembering to get the tension equation. The torque equation. Or at least looking at my notes and remembering to get it. Reminding myself of my notes. So now the interesting thing is tension is just a force, but torque is a force times a distance. And notice that at the top, I have torque. I have force times a distance, but I divide by a distance, which is going to give me force. So my units work. So now all I have to do is plug this in, and I should have the answer. So let me actually write the what everything is. So we have mg L minus mb g L over 2 divided by L sine theta. So we have G L M minus MB over 2 divided by L sine theta. All right, that looks right. So we still have a force times a distance that'll give us newtons. Excuse me, a force times the distance that'll give us torque. MGL, torque divided by our distance will give us newtons again. So we're still looking good. So we have 9.8 meters per second squared. L is 10 meters times M is 20 kilograms minus MB is 30 kilograms 30 kilograms divided by 2, so let's put 15 kilograms. And then we have L, which is 7 meters, sine 30, or excuse me, 50. I gave it 50 degrees. All right, so let's plug this in. We'll see what the tension is in the wire that's helping to hold that mass up. All right, so the tension is 91.1.4 newtons. And let's see what the x component is. Tx equals t cosine theta, which is 91.4 newtons cosine 50 degrees, which equals 58.7 newtons. And ty is going to be t sine theta, which is 91.4 newtons sine 50 degrees. So that equals 70 newtons. So 70 newtons are going up and 58.7 is going out. And if I take the square root of each of these squared, I get back my 91.378. All right, so we have and it's quite interesting that that's exactly 70. I mean, it's exactly 70, so if I pick some all right numbers, this problem. That's pretty neat. All right, so we did 2 undergraduate physics problems. We delved into angular acceleration and its 2 components, centripetal acceleration and centripetal and tangential translational acceleration. I don't remember the proper word. Acceleration T. So let's remember that when you're dealing with angular acceleration, it has 2 components. The component that's straight relative to the point, and the component that's going directly into the center. So these 2 have to add up to the total acceleration as acting on an object. So for instance, if you were making a theme park ride and you forgot one of these accelerations, you might make the ride spin too fast and hurt somebody. So you have to keep in mind all the accelerations at play so that you have all the forces involved, because again, F equals ma. So if you don't take into account all the acceleration, you won't take into account all the forces at play, and then people will be getting squeezed or pushed around harder than anticipated. And we looked at a static problem with a beam carrying a weight supported by a tension wire. And we found out, given the weight of the beam, weight of the mass, the length of the beam, where the tension is touching the beam at, we found out what tension will be caused by a slack wire that's attached at that point, making a right triangle with the beam and the wall. So 2 interesting problems. Hopefully you enjoyed. I'll have to do some form of these problems tomorrow in an exam, or my foundation exam, which will be the first exam. And then I'll have my graduate level exam, which I hope I'm prepared for. So I'll probably do some more studying on that tomorrow. So I think I'll go ahead and get some sleep and probably wake up and do some more studying for that tomorrow. Thank you all for watching who popped in. Hope you subscribe if you haven't already. Help me get to 1,000 subscribers. And I may not see you tomorrow, but I shall definitely see you on Saturday for the regularly scheduled program. And I do hope you have a nice evening.